Acceleration is a tricky subject. Mathematically, it's simple to describe. It's just the rate of change of velocity. Most people, however, do not have a lot of intuition of acceleration. Find the concept confusing. I'm going to try and give you as concise an introduction as possible and highlight the tricky bits. One powerful technique for understanding concepts is to make analogy. Here there is a clear analogy. The relationship between position and velocity is the same as the relationship between velocity and acceleration. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. So if I denote position to be x, velocity to be v, acceleration to be a, we can write that the average velocity between 2 times t2 and t1 is simply the ratio of the distance moved over the time that it took. Similarly, and the average acceleration is just the difference in velocities over the difference in times. If we take the limit of the time interval getting smaller and smaller, we get instantaneous velocity and instantaneous acceleration. Which is just the time derivative of x. Similarly, acceleration. Now, what does this symbol mean? It means that velocity is the slope of the position time graph. Well, similarly, acceleration should be the slope of the velocity time graph. So how would you go from knowing the position versus time to acceleration versus time? If I have some graph that has some shape, I can take a derivative to get velocity versus time. And then I can take the slope of that to get acceleration versus time. One of the trickiest things with acceleration is the sign. Suppose the positive direction is to the right. If I am moving to the right, then my velocity is positive. If I am speeding up, then at a later time, I'm going to be moving faster. So under this circumstance, the acceleration, which is the rate of change of velocity, should be positive. I could do a different circumstance. Suppose instead of speeding up, I was slowing down. If I'm slowing down, the velocity is going to be smaller at later times. You're going from a large positive velocity to a small positive velocity. The change is negative. This should be very intuitive. All right, now comes the tricky situation. What happens if instead of moving to the right, I'm moving to the left? If I'm moving to the left, my velocity is negative. Suppose I'm speeding up. If I'm speeding up, then the velocity is more negative at a later time. I've gone from something negative to something more negative. So the change in the velocity is negative. This is counterintuitive, that a negative acceleration is speeding you up. And the reason that is so is because you're moving in the negative direction. Now just to take it completely round, let's do the final case, which is when you are slowing down and moving to the left. So if I'm moving to the left and slowing down, then the velocity is going to be less negative at later times. If I'm changing from a large negative number to a less negative number, that change is positive. And the punchline is that the sign of the acceleration does not tell you whether you're speeding up or slowing down. Rather, the sign of the acceleration tells you the direction of the rate of change of velocity. While somewhat confusing, this is somewhat familiar from position of velocity. If I'm standing to the right of the origin and moving to the right, my velocity is positive. If I'm standing to the left of the origin and moving to the right, my velocity is still positive. In the first case, my distance from the origin is increasing, while in the second case, my distance from the origin is decreasing. Now, if the sign is tricky, it should also be tricky when the acceleration vanishes. A common misconception, a common thing which trips up students, is to incorrectly assume that the acceleration is zero whenever the velocity is zero. This, using our analogy that acceleration to velocity is velocity's position, will be analogous to saying that whenever the position is zero, the velocity must be zero. That's clearly not true. I can be moving through the origin at some speed. Right? The reason why students come up with this error in their thinking sometimes is that when you think about the velocity being zero, you intuitively say the object is not moving. And if the object is not moving, how can it be accelerating? Right? And the flaw in the logic is that instantaneously the velocity can be zero, but the velocity can be changing. The classic example of this is throwing a ball in the air. Let's treat upward as the positive directions. As this ball moves up, the velocity decreases. It's moving in the positive direction. The acceleration is negative. As the ball moves down, the velocity increases. But this time it's moving in the negative direction. The velocity is becoming more negative, and it increases in magnitude. This also corresponds to a less than zero. How about right at the top of the trajectory? Well, an instant earlier, the ball was moving up. An instant later, the ball was moving down. So the change in the velocity is negative. You're going from up to down. As a final thing, I just want to say a couple words about connecting velocity versus time graphs and acceleration versus time graph. So recall that velocity is to position as acceleration is to velocity. As we've already discussed, from a position versus time graph, you get a velocity versus time graph by taking the slope. And similarly, from a velocity versus time graph, you can make an acceleration versus time graph by taking the slope. So I could give you a problem where I give you velocity versus time. And I could ask you to come up with what the acceleration versus time graph looks like. So for example, I might give you velocity versus time, which is a number of straight line segments. The same technique we introduced for getting from position to velocity, we can use here. We break the graph into segments where the piecewise linear parts are. Over here, the acceleration is a uniform positive quantity. Over here, the acceleration is 0. Over here, it's a constant negative value. The other thing we can calculate is, given an acceleration versus time graph, we can calculate what the change of velocity is. So just as we must have, which simply means that the difference between the velocity at this point and the velocity at this point is the area of this acceleration versus time graph.